ask how to pronounce the name correctly. Today from Dartmouth College. And he's going to be, I had a friend who worked there, and she made sure that it wasn't Dartmouth University. So not to make a mistake with the name.
But there are those who love it.
Some people just like the name Dartmouth.
Dartmouth.
You can choose
okay.
them to make it your own.
Okay, so just Dartmouth. And I was just making fun of him that I should have advertised the talk in the engineering department, but it's going to be a physics talk completely because I know when we first met he said that you have all the degrees in engineering, so he's got his bachelor in electrical engineering from IIT in Bombay. I did my bachelor in the same school. So, and then MS degree in biomedical engineering from University of North Carolina in Chapel Hill, and then another science, Master of Science from MIT in Technology and Policy. And then he did his PhD in nuclear engineering from MIT and has worked basically at Harvard Medical School, Nottingham University, and MIT as a postdoc, mostly on problems of magnetic resonance and, I would say, electronic resonance, all the resonance techniques, and quantum information. And then he has been a research scientist at MIT for a number of years, and then joined the faculty at Dartmouth. And he's also a visiting faculty at IQC, which is the Center for Quantum Computing in Waterloo. And he will tell us, I guess, how to build a quantum computer, or at least how to do a quantum measurement correctly.
No.
No.
Sorry, I apologize at the beginning. Well, thank you for the invitation to come here and speak. So what I'm going to tell you about is this idea of quantum simulation. And it's going to be, in some sense, my idea of quantum simulation. If you talk to different people, you'll probably get a slightly different perspective of quantum simulation. But it's mine. It's my talk. And I can tell you what I mean and how, in our lab, we're trying to use nuclear magnetic resonance and controlling nuclear spins as a platform in which to do quantum simulation. So the whole point of this was that I didn't have to stand next. Of course, that doesn't work anymore. Okay. There we go. So first of all, starting off with the idea of the quantum promise. Many people believe we're now in the threshold of what's called the second quantum revolution. A century ago, the first quantum revolution happened where the quantum mechanics was developed, and we used quantum mechanics to understand how the world worked, how matter behaved, and it revolutionized our perspective of essentially how things are put together, how the natural world exists around us. Over the last 10 to 15 years, we're trying to develop the capabilities to actually control material, both at the nanoscale and now at the scale and at the atomic scale. So we're actually able to manufacture new molecules, engineer new devices, and at this point, you're actually starting to be able to make quantum mechanics do, or use the principles of quantum mechanics to design things at very basic level. And it's in this context that many people believe this is now the advent of a second quantum revolution. And it's almost an idea of a quantum engineering revolution where we can actually exploit our knowledge of quantum mechanics to engineer new devices, new materials, and get better understanding of the world around us as well. So some of the possibilities, of course, are in the development of quantum computers, which have the potential of the biggest potential, of course, that people ran after was solving using Shor's algorithm, which solves the factorizing problem and gives us an exponential speed up over classical computers. But quantum encryption technologies have the capability have been shown that they're in principle unbreakable, because a quantum state, if it is measured by an eavesdropper, the quantum state is changed. And so it's easy to detect eavesdropping, because when you detect a quantum system, you always change it, as far as we believe in our measurement of quantum mechanics. And you can also hopefully exploit the properties of quantum mechanics to develop new devices, new sensors that have capabilities that are ultimately not by engineering capabilities, but by the principles by the limitations of physics. For example, the Heisenberg uncertainty principle. And how far can we push metrology schemes to essentially improve technological developments that were limited by our knowledge of physics, by the principles of physics than by any other technological limitation. And finally, the one that's interesting from a physics perspective in a way is perform simulations of physical systems. When Feynman originally proposed the idea of a quantum computer in the 1980s, his initial reason for it was to actually solve and simulate the behavior of large quantum mechanical systems. He had pointed out that using a classical computer to solve quantum mechanical problems is extremely inefficient, and that you had to develop a computer that operated on the principles of quantum mechanics that would then allow you to do accurate quantum simulation. And what he meant by quantum simulation is simulate the behavior of large number of quantum mechanical particles. So what's the promise for simulation? Why would we be interested in quantum simulations? Is to understand how macroscopic behavior emerges or from microscopic properties. So in some sense, how is the sum greater than the parts in many different situations? So it's a very rough idea. And some of the most important ones are where things like where cooperative phenomena show up, where if I look at the individual level of particles, I can't really see what new physics is going to show up. But when I have a large aggregate of particles interacting together, new features develop. And some of these are quantum magnetism, high temperature superconductivity, quantum chemistry, cosmology, and ideas in quantum statistical mechanics. So there's a large push really in the last 10 years or so, again, following on this principle of our ability to now better control quantum mechanical systems, that maybe we have insights into developing quantum simulators that we didn't have before. And this is going to open the door to understanding our broader range of problems in quantum simulation. Now, there's a huge amount of promise. There's some progress, but there are a lot of caveats, of course, in terms of what we mean when we're doing quantum simulation. When we develop quantum simulators, we typically have, at some level, let's say I assume that I want to understand how high temperature superconductivity works. What people are able to do right now is implement simulations of what we believe the right model is. But the simulation is limited to our belief of what the right model is. And if you don't know what the right model is, you cannot simulate it in many situations to start with. So that's one of the challenges in many ideas in quantum simulations when you look at it, is to say, how do you know you're simulating the right physics? How do you know you're measuring the right thing, the right indicator? And these are still, we're in early days of in quantum simulation at this point in time. So there are many open questions of how making sure that we prepare the right system to study, and then make sure that we actually observe the right observables along the way as we move forward. Okay. So let me give you an idea, a little bit more concrete idea of what I mean at this point in time. So think about, of why quantum simulation is hard in this case. So think of a spin half particle in an external magnetic field. So it's just a nucleus. My eigenstates are spin up and spin down. My generic quantum state can be in superposition state, and it's normalized. So if I think of the evolution of this system, I take one ket, I map it by a unitary operator to another ket. If I'm an undergraduate student or a graduate student, and I'm simulating this on my classical computer, this is a 2x1 vector. My state is a 2x1 vector. My unitary operator is a 2x2 matrix, and I have a 2x1 vector here. This is one spin, right? If I go to n spins, my state space becomes 2 to the n spins, 2 to the n basis states, and so I have a 2 to the n by 1 vector. My unitary operator becomes 4 to the n in size, and is performing a mapping from one state vector to another state vector, right? Now, the problem that you have in quantum mechanics is that even with n equal to 12, you can see I have 4,000 elements, 16 million elements for my unitary operator now, and 4,000 elements for the state vector. If I think about what the distinction is between, now these are like n spin half particles is n qubits, so this is 12 qubit system. If I think of a 12-bit system, I only need to keep track of 12 numbers, right? In a quantum system, because I'm able to be in superposition, I need to keep track of 4,000 numbers to represent an arbitrary state in 12 qubits. Okay, that's a huge difference in terms of the number. And so if I'm operating on a classical system, I have 12 numbers. To map 12 numbers, I need a 12 by 12 matrix. Here I have an exponential growth of the size of the space, which is why quantum simulator, it's really hard to simulate systems on a classical computer. You run out of memory very quickly. The record a few years ago used to be 25 spins. The next generation of computers comes along, you get to 27 spins. You increase your computing power by another factor of 4, you get another 2 spins. It doesn't really help you go to hundreds of spins or thousands of spins, or try to understand the mesoscale physics where new properties we believe might start to emerge. So this is just reiterating this question of we have a lot of elements here. So this is why classical physics, quantum physics is hard to simulate on a classical computer. So what is the idea of quantum simulation? You think about a system you want to simulate, and typically we determine it by some Hamiltonian, HFS. I determine some initial state, psi of s. I want to evolve that state under unitary operator. That's my evolution. I have a final state, and I've got to do some detection of that final state. Now, this is another place where quantum simulation is, you've got to be careful about the promise, because remember, when we measure a system, we get one number. You make one measurement on the system. Even though you can have a large exponential Hilbert space, when you measure something, you typically measure one number. So you have to make sure that the thing that you measure is the right thing. If you have to do an exponential number of measurements to find the right answer, it doesn't help you either. So you've got to somehow do something intelligent in your detection scheme as well. So this is basically the idea. This is what we want to simulate. What do we do in a quantum simulator? We have a physical system, and we have to perform a mapping between our problem that we want to solve to the physical system that we have. There needs to be some physical system that we can map this problem onto. That mapping is represented by phi here. I now let my physical system evolve under some interaction v of p, and I create a final state psi of p, and I have to map my measurements that are made on this final state back to my problem system. Okay, this is just a very generic overview of what a quantum simulator would be. So this physical system, if I had sufficient control over it, could enable us to map this problem through this process, and we'd get some understanding about these final states here. The key is, of course, because my physical system has a different Hamiltonian, I need to coherently control the evolution of the system to get to implement that V of P. The tool that I use in the lab is nuclear magnetic resonance. So now we'll take a step back and just introduce you to the idea of nuclear magnetic resonance. It's something that's received 4 Nobel Prizes to date. It was first observed in NMR and condensed matter in the 50s by Bloch and Purcell. It's been developed rapidly in chemistry, both for regular chemistry, for structure determination, for biological studies, now for imaging as well. And the range of applications has grown. In the early days, in the 50s and 60s, NMR was primarily done in physics departments. From the 60s onwards, it moved into chemistry departments, and now it's going into biology departments and medical schools are the dominant places where people are doing NMR research at this point in time. And there's a range of applications and it's phenomenal. It keeps growing. You do NMR down in oil wells a mile under the Earth's surface to determine whether the rock is porous enough for us to recover oil. So it's a very, very versatile technique. And it relies on a couple of important features. The spin degree of freedom of these nuclei is separable from all other degrees of freedom in the system, in both liquids and solids. And the system typically has a well-defined Hamiltonian, and we have a long history of techniques in NMR developed over 50 years that allow us to control these spins very well. So again, a couple of examples. Structure determination, that's the spectrum of ethanol. This is the early days of NMR. This is constraining the structure of the amyloid protein that's believed to be present in Alzheimer's. Again, NMR measurements were critical to providing constraints on the types of structures that could be used. So you combine NMR measurements with molecular dynamic simulations, and you can get information of this type, which constrains the structure. Imaging. Now this is the original function MRI imaging experiment in which people actually looked at brain activation. The one next to it is actually from my postdoc, where I actually imaged the bone of a rabbit. So I started out doing NMR physics, and I was doing NMR of solids, but it was biological solids. It was looking at trying to do in vivo imaging of a bone, of a rabbit bone. So it's a live rabbit. And that's just an implant, a tricalcium phosphate implant that was next to it. We managed to get some decent images. You can also do engineering. This is the time course of using NMR, gas flow NMR, gas phase NMR to study the flow of gas through a coal seam. And you can actually see these various spikes that show up. That coal is a very soft material, and it pops on essentially geological timescales. So the system is something that remodels continuously. So NMR is just something it's a very versatile technique. You can study a variety of different things. Just to give you, for those of you who are unfamiliar with the technique, it's just a system of you putting a spin in a magnetic field. You can put a magnetic moment in a field. You have an energy that's given by mu dot B. You can write the Hamiltonian in terms of the spin operator coupled to a magnetic field. So you now have a Larmor frequency and the angular momentum operator here. So we put a spin in a magnetic field, and it's going to precess. So if I have a large number of spins in the system, they're all going to precess. They all precess at the Larmor frequency. But if I just put a bulk sample, let's say of water in a magnetic field, every spin has a slightly different initial phase when it starts out. And because of that, there's no net transverse magnetization. Even though they're all precessing, then if I look at the magnetization along this axis, there's no net magnetization because they're all random. But if I look at the longitudinal axis, the z-axis, the axis of the field, I can see a net magnetization here. So what we do in a magnetic resonance experiment is this. We apply an RF field, just a field that is cosinusoidally modulated, cosine omega t, that's at the Larmor frequency. And the way you do this is that you can just you have a coil, that's perpendicular to the external magnetic field, and you irradiate it with an RF pulse. Now that field can be decomposed into two components. Any oscillating field can be decomposed into two rotating fields. One that's counterclockwise rotating and one that's clockwise rotating. So I have the counterclockwise rotating field component and the clockwise rotating component. Now my spins themselves are moving at this frequency omega here. So they're moving in the same direction as one of the components and in the opposite direction as the other component here. So what you can do is if I make omega naught close to omega here, then it looks like the field is static with respect to the spins for one component, and the other component is moving at twice the frequency. And that's a standard rotating wave approximation that we make in physics frequently, is you throw away the component that's moving in the opposite direction to the spins. So then in that interaction frame, you can actually see that the effective field is just the external field that you've applied, this B1, plus some offset term due to depending on how far off resonance you are. Now all spins know how to do really is precess about the field that they observe, right? Their angular momentum, it's just angular momentum. So what they do is they see a net field, they precess about that field. And so if I'm on resonance, this term goes to 0, and I just precess about an x field. So my magnetization was initially along z. It's going to precess about this x-axis. So it's going to precess in the zy plane. And at some point, it'll be down in the y plane. And so what we consider to be a pi over 2 pulse, or 90-degree pulse, is when I keep the RF on for a time such that I have a pi over 2 rotation. And then the magnetization rotates the z to the y-axis. After which I turn my RF off, the spins keep precessing. And now the spin precesses, and I've got a time-dependent flux crossing these coils. I induce an EMF, just Faraday's law, and I detect a signal coming out. So this is the basics of the NMR experiment, of how we detect it. Okay? Just want to give you a sense of this is, what do we actually do in the lab? We turn on and off RF pulses. Our RF pulses control the spins, and then we use this coil to detect the spin. This is an inducted readout. So let's think about what happens with a simple two-spin simulator. This is a liquid state experiment. This was an experiment that was done it's over a decade ago. It's from David Corey's lab, but it's a nice illustrative experiment of a quantum simulator. So this is a molecule of dibromothiophene. The most important thing you have to remember here is this is a carbon backbone, this is sulfur, none of them have spin. There's the two bromines. We can ignore the spin on them. There's two protons are here, I and S, and they're coupled by a coupling here. Being in a liquid, the molecules tumble continuously. And when they tumble continuously, what happens is that all of the dipolar couplings between them get averaged. Any interaction that's not isotropic becomes isotropic because all the anisotropic components get averaged away in a liquid. So what you get is a Hamiltonian that looks like this. If I have two spins, I have omega I, IZ, omega S, SC, and a coupling between the spins that's given by this J coupling, JICSC. If I think about the energy level structure, they're both protons, so the omega I and omega S are both large compared to J. They're in a relatively high field. But they're different because the presence of the bromine here actually makes the resonance frequency different for these two. So you have a 4-level system, and the eigenstates are up, 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 down, 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 and down, up. And they have slightly different energies. If you do the NMR spectrum, get an NMR spectrum, you'll see 4 different peaks here. So let's say what we wanted to simulate. That's my physical system. So, oops. I knew I was going to hit the wrong button. So that's the system this is my physical system. This is the system I want to simulate. So I'm going to think about a quantum harmonic oscillator, just a very simple experiment. So in a quantum harmonic oscillator, I have, that's the Hamiltonian. And I can think of the spectral decomposition of the Hamiltonian as given in terms of n plus 1/2 omega nn. Now it's an infinite ladder of states. Now clearly I cannot simulate a full harmonic oscillator with a 4-level system because I've got a 4-level system. I have a finite dimensional system and an infinite dimensional system here. It doesn't work. But what we could do is try to simulate a truncated harmonic oscillator, which would then have, the truncated harmonic oscillator would have a Hamiltonian that's given by this, just the first 4 levels, right? I'm using n over n plus half. If I take the factor of 1/2, I have 1, 3, 5, 7. So now what I need to do a quantum simulation is, once again, the first step is to map my problem from this problem I want to solve to the physical problem. And so that's the mapping we do, is we take these are the 4 eigenstates of my physical system, and I map them onto the n equal to 0, 1, 2, and 3 states. Now this is not a unique mapping, but this is just one we can choose at this point in time. The nice thing about this is that if you start with the up-up state, you can see that by n equal to 1, you flip 1 spin, n equal to 2, you flip 1 more spin, and n equal to 3, you flip the spin back. Okay, so these are 4 distinct states. Now you can rewrite this in terms of the spin as the spin operators as this Hamiltonian here. Ht is just 2 omega times identity minus Iz minus IzSc. Now a physical system has a Hamiltonian given by this. Is omega I Iz, omega S Sc, and J IzSc. So we need to somehow transform this state, this effective Hamiltonian, into this effective Hamiltonian. How do we do that? So we can go into an interaction frame defined by frequency omega 0, and in an NMR spectrometer, your radio frequency pulse quite often provides that interaction frame. So in an interaction frame, it's just omega I minus omega. You just subtract omega naught from both of these, and this term is invariant to the change. And if I let my interaction frame be exactly at omega s, this term drops out. So I just have an interaction Hamiltonian that's given by omega I minus omega s Ic. Now my target Hamiltonian is still this term here. I can ignore the identity because the evolution identity of the identity is essential. There is no evolution under the identity. Okay, I want to obtain these 2 terms here, but they have equal magnitudes. The terms in front of Iz and IzSc are equal. Here the 2 terms are different, right? As you can see here. The coefficient in front of the Iz term is a frequency difference. The coefficient in front of the IzSc term is just a coupling strength. Okay. So what we do here is we apply a set of pi pulses. So a pi pulse can flip a spin from, let's say, z to minus z or x to minus x. So what does this do? If I apply a pi pulse to the spin, think about just this pi pulse here. This pi pulse would flip the Iz term to the minus Iz, but it's applied to both I and S spins. So if I flip both of these from Iz to minus Iz and Sc to minus Sc, the 2 negative signs cancel. So this term is invariant to the flip of the pi pulse. This one is not. So if I look at the evolution for this time period tau 1, the evolution during this time is completely cancelled during this time for this first term here, but for the j term, it actually adds because the pi essentially it looks as if the pi pulse has no net effect. So the net effective Hamiltonian at the end of this time is just the frequency difference only operates during this tau 2 time, the unbalanced time. So it's tau 2. So fractionally, it's the time frame, the fraction tau 2 over tau 1 plus tau 2, for which this the first term IZ operates, and the j term operates the entire time frame, tau 1 plus tau 2. So now I have a way to experimentally change the ratio between these two, because tau 1 and tau 1 plus tau 2, tau 1 and tau 2 are experimental knobs that I have in my system. I can change them. Okay. So if I set tau 2 over tau 1 plus tau 2 to be this ratio, j over omega I minus omega s, I get exactly this Hamiltonian here. I make these two coefficients equal, which means I've implemented this Hamiltonian. So these are experimental results done with 3 initial states. So let's say initial state is being the 0 state. There's no evolution. My initial state is a superposition of the 0 state and the 2 state. So I'll have oscillations at 2 omega, and this is what you see. If my initial state is a superposition of all four states, 0, 1, 2, and 3, I should see oscillations at, depending on the overall evolution, will show oscillations at omega, 2 omega, and 3 omega, right? Because there's a frequency difference omega between each successive pair. There's a frequency difference of 2 omega between all these pairs, and of 3 omega between these two. Now, this is where you then have to think about what does quantum measurement do? It measures one thing. I don't just measure the state. There's no such thing as measuring the state. I measure an observable. So I've got to pick which observable I'm going to measure, and that's going to report on one aspect of the evolution of the final state. So depending on the observable, I can detect states that evolve as omega or 3 omega. And that the consequence of this is that this just depends on the observable we chose to read out that state. Okay. But what you can see is that we're getting exactly the types of evolutions that we can see. We've mapped the Hamiltonian of the 2-spin system onto the Hamiltonian of the truncated harmonic oscillator. So this is a very simple, this is an experiment from 1999. It's one of the first quantum simulation experiments that was done. So just to provide an overall perspective again of where this fits in, this is our system that we wanted to simulate, the quantum harmonic oscillator. This is our physical system. So in the same picture that we had before, this is a problem that we wanted to solve. We mapped it onto this problem, the physical system. And this V that we implemented is done by a set of pulses by which we effectively engineer a different Hamiltonian for the system to evolve under. Okay. It's nice. Liquid state NMR simulators, like the one I showed you with small numbers of spins, are very useful because you can do universal control, which means I can implement any unitary operator in the system. But it works only for small spin systems. When I get to a larger number of spins, it's you don't have that ability of control. Liquid state NMR tends not to be very effective as you become a larger number of spins. But some things have been studied. Things like people have tried to simulate the ground state of the hydrogen molecule. There have been claims about criticality in small spin chains. I don't know what criticality is in a small spin chain.
Could you go back?
Yep.
You have a spin system.
Yep.
And you do the measurement, which of course destroys the quantum state.
Yeah.
And basically you do the measurement at different frequency, and you see what the readout is at the different frequency on different systems.
Yes. Effectively, you restart the experiment. So if I want to go back for a second.
Okay.
So essentially what you're doing in each one of these is a completely different experiment. Each point would be a completely different experiment. You'd restart from the initial state, re-prepare the system.
Same initial state.
Sorry, right? Right. You'd go back to the initial state, evolve for a little bit longer time, then perform the measurement.
And when you perform the measurement, of course, that destroys the state.
And destroy state. Now we're doing, this is still an ensemble measurement because we're doing this on a liquid state system. So there's essentially, it's Avogadro's number of spins simultaneously being measured. So what you're doing is you're essentially doing an expectation value measurement of the system. It's not a projective measurement in this experiment. Does that help? Yeah, yeah. Yeah, so that's an important point actually. So in magnetic resonance, our ability to detect, the number of spins we can detect is the h bar omega is very small compared to kT. So h bar omega is typically in the microkelvin range. And so what we measure here is large 10 to the 18 to 10 to the 22 spins is typically what is measured in an ensemble of that size. So we're far away from the ability of measuring, doing a projective measurement on a single quantum system. So go to larger systems, we want to move to the solid state. The solid state allows us, in the liquid state, we have this problem of diffusion and motions it makes each molecule isolated, but it limits what you can do in terms of the size of system that you can grow. In the solid state, I can take the physicist's favorite sample, which is a dielectric called calcium fluoride, and the fluorine spins form a nice cubic lattice. They're all spin 1/2 particles in a nice cubic lattice. And we put them in a magnetic field. And the Hamiltonian of the system has two major components, a Zeeman component and the dipolar component. The Zeeman is just the coupling to the external magnetic field. And the dipolar component that I've written here is the truncated dipolar component. It's a part of the dipolar Hamiltonian that commutes with the Zeeman field. Because the dipolar coupling coefficients here are on the order of kilohertz, tenths of kilohertz. The Zeeman frequencies we're using here are typically on the order of hundreds of megahertz. So a large energy scale difference, and which is why we can truncate the dipolar Hamiltonian and only keep those components that commute with the Zeeman term. Now the coefficients here, the coupling between spins depends on the distance between two spins. It's 1 over r cubed, but there's also an anisotropy that comes in because of your strong quantizing field. There's the large Zeeman field that we've applied to the system. So in the solid state, what we have is our nuclear positions are fixed, dipolar couplings are relatively strong. We have a very large number of spins, but as opposed to in the liquid state, we could go in and actually probe each spin individually and say, okay, what does this spin do? What does that spin do? Here we only have our collective control of all the spins. Now NMR has, there have been two classic many-body problems in solid-state NMR. One is the idea of spin diffusion, which was postulated by Bloomberg to explain, T1 relaxation times in solids. It was initially thought that T1 times of nuclear spins in solids would be very, very long because the coupling to phonons is so small. But Bloomberg showed that actually what happens is that the spins, it's the electrons defects that are in these systems that couple to the phonons and relax quickly, and nuclear spins actually diffuse. The polarization of nuclear spins diffuse through the lattice by flip-flop interactions and to the sites of these sinks, electron sinks, and that's how they relax the lattice. So that was, and again, it's the spin diffusion happens because of this dipolar Hamiltonian here. There's a IX plus IY term in here that produces a flip-flop. The other one was the free induction decay, which is the collective response of the spins to a pi over 2 pulse. So we talked about I mentioned the pi over 2 pulse where I just flip all the spins from the z-axis to, let's say, the x or y axis. And if you look at the response of the system, if you just measure the belt magnetization after that, you just see the signal will decay fairly quickly on the time scale of 50 to 100 microseconds, and maybe with an oscillation depending on the orientation of the crystal with respect to the external field. And there's a fair number of amount of theoretical work to study what happens. What is the nature of the many-body physics that happens in both of these systems? So I want to introduce you to one tool quickly here, to an idea called multiple quantum coherence. I'll explain what it is, because I'm going to use it in the next slide. So if I think about M1 and M2 being two to being basis states let's say the Z basis being the Zeeman basis, then what I call the coherence order of a superposition state Y as AM1 plus BM2 is just a difference between M1 and M2. So it's N is equal to M1 minus M2. So if I think of the density operator or the state operator corresponding to this Y, it's just the outer product, the projector. And you'll see that it has the M1, M1 term, M2, 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 M1, and M1, M2. The way we can get information about this coherence order here, N, which is the difference M1 minus M2, is by doing a collective rotation of this density operator by about the z-axis by an angle phi. So if I rotate this by about the z-axis by this angle phi, this term and this term are going to give me no net phase because I'll get a plus M1 phi and a minus M1 phi here. But these two terms are going to give us plus or minus N phi. Okay? I'm going to pick up a phase from these two terms. And it turns out that those N and phi become Fourier conjugate variables. So what I can do in an experiment is to sample phi, it's under my experimental control, from 0 to 2 pi systematically, and then Fourier transform the data with respect to phi to get a distribution of N, which tells me what are the types of coherences I have, what are the ranks of the coherences I have in the physical system. Okay? This distribution reports then on the spin-spin correlations, because in order to get, if I have a large number of spin half particles, in order to get large differences, I need large numbers of spins that are interacting together, right? Because it's just an addition of angular momentum that's going to allow that. So this is an experiment that we did on, again, the solid state, the free induction decay in the solid. So this is the normal magnetization decay that we've seen. This is the magnetization just decays on the order scale of 50 to 100 microseconds. Now what we did in this experiment is something different. We applied our pi over 2 pulse, allowed the system to evolve for some period of time. Then we applied the basis encoding. We rotated the system about the x-axis by an angle phi. And then by using NMR control, by using pulse sequences, we implemented the dagger, the time reversal component, or the negative of the Hamiltonian, if you wish, to refocus this evolution here. So during this evolution AUD here, we create multi-spin correlated states. We tag them with this rotation operator, and then we refocus them, because the only thing I can measure is a single spin operator, something that has a dipole moment. Okay, because I'm using a coil, I can only detect dipoles. And then I get an echo here, and I repeat this experiment for multiple values of phi, as I said earlier, and take the Fourier transform. And that Fourier transform tells me about the size of the spin cluster that I've created under this dipole evolution. And if we do this experiment for different periods of time, we can see that at short times, I have very low rank correlations. I only have maybe 2 spins coupling together. As I go further out in time, I can see 6 to 8 spins, 12 spins, and here we can see even at about 170 microseconds, the free induction decay, the magnetization has gone to 0, but I still have complete coherent control over the spin system. I can let the spins evolve out here, tag them, and refocus the system all the way back, and I can see that I've got over 20 correlated spins in the system. It's a highly coherent evolution that's taking place in the system. Okay. And so this is the first experiment in which we were able to show that the system stays very coherent for a long period of time, because the support on our observable subspace is decaying very quickly. So in terms of, we can only observe certain things easily, and those terms decayed quickly. So we sort of were neglecting what was happening in unobservable parts of the Hilbert space. But if I tag them indirectly and then refocus them back, I'm able to get more information about what's going on in the system. Okay. We can actually see, you can see the growth of the spin system. This is the 0 and the 2 actually represents the idea of almost 2 spins. If I have 2 spins coupled together, they're going to go flopping back and forth. So there's going to be an oscillation initially. But if I let them grow for longer periods of time, I can see the 4 spin correlations, the 6, and you can see there's a very steady increase. Now this is, this is the first time we had this data on showing the growth of fairly large size spin clusters in NMR. This is all room temperature. What could we do with this data? Unfortunately, not much, because it's a many-body quantum system. We talked to some theory colleagues, and they said, well, it's a many-body quantum system. where there are limits to what we can measure. We can sort of go to hydrodynamic limits and talk about large-scale properties and flows, but we can't actually help you interpret this data beyond that. So it goes back to this question of quantum simulations. So how do we understand data like this? I have interesting data, but there's a challenge to thinking about what's the theory that's underlying it. We know it's Hamiltonian dynamics. And so we moved to a system that was a little bit different. Is to say, let's go closer to a system that a theorist could solve. And all solvable many-body systems, or almost all solvable many-body systems, are in one dimension. 2 dimensions, you can solve a couple of problems. But in one-dimensional systems, you have a class of solvable problems. So go to the simplest model, something like the XX model. Could we implement something like that was our goal. The XX model just has a Hamiltonian like this. It's just Ix plus Iy. It's a spin chain. Every spin is coupled only by to its nearest neighbors. And you can rewrite this in terms of ladder operators as I plus I minus plus I minus I plus. It turns out that this can be solved by the Jordan-Wigner transformation to spin-free fermions, and this was done many years ago. And you can solve this, and you get a Hamiltonian that looks like this. And it's interesting this Hamiltonian's been interested from a perspective of quantum information as well, because it's been suggested that you could use this system as the spin chain as a way to transfer information from one part of a quantum computer to another. So Alice could load up a quantum state on one end here, and sometime later, Bob could pick up that same state over here. And the reason we were able to actually, this proposal was viable was because you could actually go in and solve the full system analytically. It's a well-defined, it's a system that is completely solvable. Such a system can also move magnetization down this. It doesn't just move quantum states, arbitrary quantum states. I can create initial state, thermal state that looks like this, identity minus epsilon IZ1, where essentially think of this as a magnetic moment on spin 1. And I let the system evolve, and it just ballistically moves through the system at a uniform velocity, bounces off the end, and I see some interferences at that point in time. This is a simulation of 25 spins. So our model system now, we want to try and implement something like that experimentally. So we went to a system is fluorapatite, which is this crystal. Fluorapatite turns out to be the crystal in your teeth. It's if you've been brushing with fluoride toothpaste all your life, your teeth turn from hydroxyapatite to fluorapatite. So in fluorapatite, what you have is the fluorine spins form nice spin chains. The distance between fluorine spins within a chain is 3.4 angstroms. The distance between chains is 9.4 angstroms or so. Now, the dipolar coupling, remember, is 1 over r cubed, and it also has this orientation dependence theta ij. So if I orient the chains along the magnetic field, I can get a ratio of the in-chain coupling to the cross-chain coupling of about a factor of 40. I can also get for free the fact that the next nearest neighbor coupling is about a factor of 8 smaller than the nearest neighbor coupling. So in a limited time regime, and that's actually an image of the crystal, in a limited time regime, this approximates a nearest neighbor coupled chain. If I restrict my studies to shorter time scales. So my Hamiltonian goes from something like this. I can pull omega out and say that each spin is only coupled to its nearest neighbor. It's still the dipolar Hamiltonian. Sorry. Oops. It's still this Hamiltonian. It's not the XX Hamiltonian that I showed you before. What we can do, however, is using pulse techniques, we can create what's called the double quantum Hamiltonian. And that has this form here. It's Ix minus Iy. It's a little bit different from the XX, but we can't create the XX in the lab. We can create the XX minus Yy, which is we call the double quantum Hamiltonian in the lab. So by 1D geometry, we can pull this omega out of the sum, and then by coherent averaging techniques, by pulses, I can create this Hamiltonian. So what we can do here is, because the double quantum Hamiltonian, this Hamiltonian and the XX one are related by similarity transformation, you can think of it as just flipping every alternate spin. They essentially have the same eigenvalues, and so I can use the dq to simulate the effect of the XX. And the first person who showed the solution to this is Feldman and LaSalle. So Okay, just to give you an idea of quickly of how we do how do we do the transformation of the Hamiltonian in this case. So our coherent averaging is given in this by this way. So I have an evolution delta over 2. I apply a pulse about the x-axis. I have an evolution 2 delta. I have a pulse pi over 2 about the minus x-axis, another evolution delta over 2. And the evolution, there are free evolutions under this dipole Hamiltonian here. So if I just sort of string along all my unitary operators, okay, just say, okay, this delta over 2 just corresponds to this unitary evolution. It's piecewise constant. This rotation is this operator here. This 2 delta is this piece here. This pi over 2 is this rotation operator here. And this delta over 2 is this evolution here. I'm just going to string them all together. If I look at it more closely, you can see that I have a rotation, an evolution, and another rotation. So I can think of this as rotating the Hamiltonian. So I can rotate the Hamiltonian HD about the x-axis by pi over 2, which basically takes z to y. The dot product is a rotational invariant. So I get this term. And now if I think about it, I've got an evolution of delta over 2 under the dipolar Hamiltonian, delta over 2 under the dipolar Hamiltonian, and 2 delta under this. So I'm just going to sum them up in the average Hamiltonian sense. And I get a Hamiltonian that looks like that. Now, why does this work? If I make it stroboscopic and periodic, it turns out there's something called the Magnus expansion. You can make this rigorous, that if you make your pulses short, if you make your cycles short, the sequence converges very quickly to this effective Hamiltonian. And this process works fairly rigorously. So this is magnetization transfer under the double quantum Hamiltonian. So once again, let's say I take my magnetic moment and put on the first spin. I let my system evolve under HDQ. And this is the simulation the corresponding simulation for the DQ Hamiltonian. Because of the similarity transformation, you can see that the spin flips every alternate site as it moves down the chain at constant velocity. Now remember, as I said, when we detect these spins as well, we can only detect the collective spin, all of the spins together. So what I'm doing is I need to sum over this entire axis, project everything, and just measure that as a function of time. That gives me this curve. This is at long times. This is a simulation for 25 spins once again. And you can see that the signal decays, it oscillates, but it hits the boundary again. I can see this large recurrence, and then I can see the interference effects. But if I look at just focus on the short-term behavior before I reach the boundary, I can see this decay and an oscillation here. This is our experimental data in the fluoroapatite system where we did the same experiment. You can see the decay and the oscillation. The curve is a fit to the analytical model with free fermions, and the squares are the experimental data. We get a very nice fit between the model of the free fermion model and our experimental data in the system. We can go further than that. We can actually say what are the two-spin correlations present in the system. So in this as the spins move through the system, they go back and forth between sigma z states and sigma x, sigma y states. We can actually indirectly measure the sigma x, sigma y states as well, and we see that they oscillate 90 degrees out of phase with the sigma z's. And so this is for two initial states. We can see this is for a magnetic moment on one end. This is for the thermal polarized state where every spin has, where you can think of a uniform distribution of magnetic moments everywhere. And the fit to the analytical expressions are very good. Up to about 800 microseconds to about a millisecond is when we start to see the behavior, the appearance of these long-range correlations. The fact that my system is really an approximation to a 1D system. It's not a true 1D system. It's an approximation because I'm ignoring the long-range couplings, I'm ignoring cross-chain couplings, and all of those things. But so the model, I expect the model to break down, but at short time, it really is a very good model of a free fermion solution of a spin chain. We can also have access to other observables. So, when we do simulations, we have to think about what observables do we care about, what are the things we can calculate, what are the things we can measure. And hopefully there's an overlap between those two, right? So here's the analytical solution tells us that the operator forms have two types. There are two types of operator forms, these C dagger, and CC. These are fermion operators, and C dagger C operators. If I represent these as spins, they look like this. The C dagger terms look like sigma plus, a whole bunch of sigma z's, and a sigma plus. The CC's look like sigma minus, a whole bunch of sigma z's, and a sigma minus. The other terms, the C dagger C's, look like sigma plus, sigma minus, with a bunch of sigma z's in the middle. If I rotate this about the z-axis, I can only get a plus 2 phi or a minus 2 phi here, or no phase. That's why these are called 0 quantum, these are called 2 quantum. And in the z basis encoding, so initial state, again, I do my double quantum evolution, I rotate, in this case about the z-axis, in this case about the x-axis, and I time reverse my evolution. And again, this is where you need to have control over the quantum system. If I couldn't time reverse my evolution, I couldn't make these measurements. But because I can time reverse the evolution and create essentially what's called a Low-Schmidt echo, I'm able to actually measure the evolution, these multi-spin correlations. So you can see that, again, this is the data for the double and 0 quantum. And at short times, it's a perfect fit the analytical result. At some point, you start to see a decay, and you actually start to see the growth of higher spin correlations, 4 quantum and 6 quantum. These are due only to long-range couplings. These do not exist in the analytical model. There's no space here for the long-range correlation, for the higher order correlations here, the 4 and 6. They only show up because our models break down. I could also take these operators and re-quantize them in an X basis, and this X basis experiment tells us what's happening. So now this tells me about the number of operators that are present in this string. So if I rewrite this in the X basis, each one of these becomes a sum, and I get a binomial. Let's say I have sigma plus and sigma minus in the X basis, and I get what looks like a binomial distribution of the X in the X basis. So I can see that I get 1 spin operators, 3 spin operators, 5 spin operators, and 7 spin operators. But really, the growth of operators is actually fairly slow. There's a finite growth in operator space, and then it stays fairly constant, which is actually fairly typical in an integrable system like this. We don't have an exponential growth in operator space. So here, going back to our model, we can do our model system was the XX Hamiltonian. We wanted to understand the evolution here. This is a solvable system. We mapped it onto something that our physical system here, with using coherent coherent averaging theory to implement the right Hamiltonian here. And we were finally able to detect systems that we cared about. So as we move further, we can now think about how do we perturb this dynamic. Okay, we went from something that we couldn't understand at all to something that we can understand, we already knew the answer to. So can we do something in the middle here? And this is partly where we want to go next, and we're starting to do this. And I'll go through this very quickly, because a lot of this is preliminary. It's to say, let's add, this is the regular pulse sequence for the double quantum Hamiltonian. But I can add some additional phase shifts, which introduce then what look like perturbations to the system, where the perturbation has this form here. We can run experiments with the various perturbations and actually see the dynamics change of the magnetization. Now, it turns out that kick-spin chains, this is something that's called a kick-spin chain. The kick-spin chain is really interesting because Prozin has actually shown, it's been shown theoretically that in an Ising system, if you kick an Ising system, if you kick it with the right symmetry, you can move it from a regime where it's integrable to a regime where it starts to show quantum chaos behavior. And so you can actually tune a system from what's regular behavior, which is analytically solvable, to behavior where it's no longer analytically solvable. And you can do this with a controllable parameter. And here we have, for the first time, I'm hoping, the ability to, by changing these experimental perturbations, we'll be able to tune a system across this boundary and observe how the behavior and the dynamics change. And that's really important from the perspective of quantum statistical mechanics, because mixing systems are what eventually give rise, what we believe gives rise to ergodicity and thermalization of quantum systems. So again, this turns out to be a staggered local field in this additional term of the Hamiltonian. Is that every site has an extra field, but the sign changes according to sites. We can randomize these as well to create what simulates an open quantum system. So a spin chain that's coupled to a bath that's fluctuating bath. So we can simulate those effects as well in this model now. So there's a large landscape we start to get to play with by first anchoring our system in a place where we know the answer well. We trust our answer. And then we want to slowly break it. Because at that point, I trust whatever I see. Because if I'm going to be able to, if I want to move into a regime where I have new physics or expect to see new physics, I need to first make sure that my system is robust. And that's what we've sort of shown our system is robust, and now we've moved beyond that into regimes where we start to see behavior that's different. And we're not completely sure how different and why different yet, because that's still part of where the research is going at this point in time. But that's my picture of quantum simulations, that you have to first anchor in problems that you know the answer to. And then you move beyond those into places where you don't know the answer, and then hopefully to extract some information about those new systems. So here, this just says that as we increase the noise strength, we go from original modulation, original oscillation here, to something that starts to just level out. And this is just very preliminary data. We also have indications that if I do something like a Low-Schmidt echo, I evolve without perturbations and then with perturbations. My echoes seem to occur at later and later times, which means which seems to suggest that my velocity of my excitations is slowing down as I introduce noise into the system. So this is very preliminary data, though, but it's suggestive right now that we're actually able to tune the behavior of the system in a fairly controlled way. And I think I'm going to stop there. Now, the next step is, ultimately, we'd like to move to engineered systems. So rather than using a natural crystal, I'd like to be able to take, for example, a silicon lattice, implant a chain of phosphorus atoms in a nice one-dimensional chain, or maybe even 2 dimensions, whatever low dimensionality I want using E-beam lithography, and tune the couplings by the distance spacing, and use more sensitive techniques that actually detect single quantum states at this point in time. So, for summary, magnetic resonance gives us well-defined Hamiltonians. That's really the strength of it. We have long coherence times. In principle, in solid states, we can do large spin simulations. We have really very, very good control over our system. It's restricted. We can only do collective control. But what we can do really, really well. And we can study both statics and dynamics in the system. And I think this restriction comes in all types of quantum simulations. There are only certain initial states we can prepare. There are only certain types of Hamiltonians we're going to naturally be able to implement. And there are only certain things that we can measure easily. If I need an endpoint correlation function, as an experimentalist, I don't know how to go in there and get it. I need to map that onto an observable in some way, some easy way. And maybe using that, I can track that back into some other parameter that's calculated, essentially. And acknowledgements. So a lot of this work was done primarily with Paolo Capellaro and David Corey's longtime collaborator, Lorenzo Viola at Dartmouth, and then the newer work has been done with a couple of other grad students who are unfortunately not here yet. But thank you.
Questions?
Yeah.
So you're doing spin systems. Are there people doing similar experiments with electronic systems, with Joseph Johnson?
So Andrew Hoke at Princeton is using superconducting circuits and to get arrays of Josephson junction circuits to do quantum simulations.
So they're not working in this collective regime of those, or?
I don't know the details of his experiment. Whether he's, in principle, you can do a lot of experiments done with collective control. In principle, if you can have access to local gates. You could probably tune each local gate, or I could flux couple a particular gate and move it in and out of resonance, for example. So one of the advantages, for example, in a set of superconducting qubits that are coupled together, if I had a local bias field or a local gate, I could keep them all. In principle, I could tune them all to the same energy splitting, and then I could go in and move one of them out, and then address that spin separately. In that sense, it would not be collective. I would be able to identify a single element in that overall chain. So I think that's that's one difference that you would get in that system, that you could potentially get, I should say, in that system. I think in terms of long coherence times, people are also suggesting things like NV systems and nitrogen vacancy systems. The challenge there, so people are implanted arrays of nitrogen vacancy defects. The challenge there is that the NV axis is random. There's 4 different possibilities for the NV axis. I can implant a nitrogen vacancy, but when I create an NV defect, because of the sp4 hybridization, I can have my defect here or any of these 4. The axis of the NV could be any of the 4 tetrahedral axes, and the Hamiltonian changes based on that symmetry. And so you can have non-equivalent states, and that's a challenge that they have. If you put them in a magnetic field, which you may then make the field the major quantizing axis, that would change. That would help that system, but it changes in physics quite a lot in that case.
Are there constraints in terms of the controls you mentioned?
Yeah.
Are there constraints which are not part of traditional quantum mechanics? And if so, what are they?
I'm not sure I know what you mean by constraints that are not part of regular quantum mechanics.
You mentioned that one has to be careful and abide by controls, etc.
Yeah. So
These controls constitute other than traditional quantum mechanics constraints or limitations.
So the 2 main constraints I would say are these. One is, which I think is the answer to your question, is we have to respect the symmetries of the system. So if my control is over the collective degree of freedom, the only thing I can do is collectively rotate, manipulate my Hamiltonians. I can go into a space which is not constrained within the algebra of those collective rotations. The second part of it is to say, what is the, is more engineering in a way, is to say, can I implement my controls well enough so that the convergence to the average Hamiltonian idea that I showed earlier is valid. So that would be another constraint, which then says, what I showed earlier is assumed almost a delta pulse approximation for my control, which is my rotations are instantaneous compared to, and that I can ignore the internal Hamiltonian during my rotations, for example. Now those work very, very well if I have enough power and if there's a sufficient separation of scales between the rotations. If that's not true, the sequence doesn't converge, you start to get more errors, and also you start to so let me leave it at that. So you start to get more errors in terms of what you can do. So what you implement is different from what you think you're implementing. We can engineer some of those out to a little bit, to some degree, but there are physical constraints in terms of what I'm able to do in the lab. Yeah.
Can you give us an honest assessment whether we will have a quantum computer in the next 20 years?
What do you mean by a quantum computer is almost a question to ask, right?
By honest.
That's a harder question to answer. Or a question to answer would be, if you had a quantum computer, how would you know you had one? That's actually the problem that D-Wave has today. So D-Wave is this company out of Vancouver who claims that they built a 16-qubit quantum computer with simultaneous qubits, and it can simulate. It appears to do simulation problems, optimization problems faster than current computers can. We don't know whether they've got a better classical algorithm, or it's implementing some mix of a classical or quantum algorithm, or if it's truly quantum mechanical everywhere. How do you
know, or they don't know?
They don't know. We don't know. No one knows. The data, they're saying it. Google has bought one. A couple of other companies have bought them because there's.
USC doesn't need it, but someone bought it to USC.
Yes, well, they donated it, yeah. And there's somebody else who has one too. And so there's evidence that it's doing something. What it's doing, we don't know at this point. Because you're taking a system, they're implementing what's called adiabatic quantum computing, right? Now, they've got to make sure that They don't create any excitations along that adiabatic passage. Its systems truly staying adiabatic. We don't know the Hamiltonian of the system and what the size of the gap is. So it's hard. How do I tell? And the end result is, it looks like it's doing something useful though. If that's a good answer, then, and actually it's turning out to become, it's spurring more interest in the field. It's like, suppose you built something. How would you know that you had a good scalable quantum computer? As you get, because how do you test some of these things? Because suppose I had n qubits. Let's just say I have an n qubit system. The way we do tomography is one way that people think about doing benchmarking. Tomography just says, I want to implement this unitary operator. What unitary operator did I implement? So to do that, I need to send in a full basis of states on the input, measure what the output is. But when I measure the output, I don't know what I'm measuring, so I need to actually do tomography of the final states for each final state, for each initial state. So reconstruct the final states for each initial state, and then put a full basis of initial states. If I have an exponentially large Hilbert space, that's a very hard thing to do. It takes, so how do you benchmark and know that you're doing something useful? That's hard.
Factorization.
Right. So you could say if it works, yeah.
You could do that as a test.
Right.
You know
Yep.
the answer.
Right.
Well,
You could figure out the answer. It's an NP problem, which is nice that you know the answer. You can test the answer. If you,
Any other question?
Yeah.
So, moving forward, can you comment briefly on how NMR methods compare to other quantum simulation methods, such as trapped atoms, or the like, in terms of things like tunability and the classic Hamiltonian tests?
So, they have advantages and disadvantages. We have an AMO person in our faculty in our lab, Kevin Wright, in our department, Kevin Wright, and we've talked about the fact that they spend a lot of time getting their system set up cleanly. But the types of manipulations they do are much simpler in a way. They can tune on and off interactions in a certain time scale, and then they make measurements in, they make some very precise measurements, very nice measurements in a way. I would say the difference we have here is this is already naturally a large system. The regularity of the natural lattices is very strong. Our control is very good. The limitations I have right now is in terms of sensitivity. If I'm worried about pure states, we don't have access to pure states. And there's questions, I think, for both. Observables are a problem for both, which is your limited access of observables. In principle, you have universal control in an optical system. But in a full 2D lattice, I don't know if you do have universal control. I don't know if it's been that if you can go in and actually rotate an create an individual atomic lattice position. Well, because that site-specific addressing is harder to do. I think at this point in time, there's probably a little bit more. There's a broader range of Hamiltonians you can engineer with AMO. I think the NMR spin physics for spin lattices, I would say this is a very robust tool. If you ask me to do a general gauge field or something like some other type of simulation, we can't do that necessarily with NMR. But I can do spin lattices. I can do a variety of spin Hamiltonians. We can think about ways of doing X, Y, Z, or different other Hamiltonians of that form. But other systems, I would say we're more restricted in a way.